Right. So before we begin our lecture, just want to ask you guys if you have any question. I think last Tuesday we have gone through on the last part of chapter 3, which is on coatings, on press current methods, cathodic protection, anodic protection. What does it mean by cathodic protection and anodic protection? So of course, if you still remember, cathodic protection means that the metal to be protected will become cathodes. In this method, we will pair it with metal that is more reactive. That eventually will become anode, and this actually will be called as sacrificial anodes. Some examples would be like magnesium, zinc, and aluminium sacrificial anodes. And other than that, we have anodic protection. Anodic protection can be, I think, classified a very special protection because if cathodic protection is not effective, especially in acidic and highly alkaline condition, then anodic protection will be applied. In this case, metal to be protected will become anode. The concept is basically making anode to passivate first. I mean, oxidize to form a passive layer. Then when it forms a passive layer, it cannot undergo further oxidation or further corrosion. And then we have the last method, which is on a proper design. Of course, a proper design is needed to prevent mechanical damage to the structure, especially due to erosion. And I believe last Tuesday also we have started our chapter 4, which is on the electrochemical reactions and kinetic. We have gone through a few things, especially on, let me add the jihad first. Okay. Especially on the rate of reaction related to corrosion. Then we also have understand that in electrochemical process is always related with charge transfer, mass transfer, I think phenomenon. And last Tuesday we have gone through this. I guess this actually the essential part of last Tuesday's lecture, which is on the electrochemical double layer. So what does it mean by electrochemical double layer? It means that a layer of solution that is produced, which have a different composition from the bulk solution. Okay, so we have a few models like Helmholtz model, Goy-Chapman, and also Stern model. So for the Helmholtz model, if you still remember, what does it mean by Helmholtz model? So anyone can recap. Perhaps those who joined the lecture. Jihad, how are you? Jihad, okay, maybe mic is not functioning. Mahdi, can you tell a bit what you can understand with Helmholtz model? What have you learned? Mahdi?
The electrostatics interaction between the surface and the counters ions in the solution, and the linear potential of the surface to be outer.
Okay. Basically for Helmholtz model, as I said, it accounts the first mode of mass transfer, which is migration, because if you still remember, migration happens due to electrostatic interaction. This what we have, I think, learned in chapter 1 for mass transfer. Okay. So migration happens because if you have, I think, for example, over here, okay, electrodes, when it oxidizes, become positively charged, and then it attracts another species of anions to come closer to the surface. So this actually related with electrostatic interaction. So anything that deals with electrostatic interaction, the model of double layer produced is basically referred to Helmholtz model. And of course, as I said, it will form a double layer, okay, which is a capacitor, and then the potential values will have a linear drop, because over here you will notice that um, the region near to the inner Helmholtz plane will have a higher potential value as compared to further to outer Helmholtz plane. So that is why the potential value is actually showing a linear drop. But Helmholtz model actually didn't account certain things like thermal motion, the temperature effect, diffusion, and other things. Okay, but the other advancement will be Gauss-Chapman, because the Gauss-Chapman actually accounts diffusion. So Gauss-Chapman believed that if migration didn't happen, then I think the ion is actually more or less been diffused to the electrode surface. So this actually will create a flat and infinite surface. Okay, and then it also accounts the thermal motion, because diffusion actually happens due to several factors, including like thermal motion. And the other thing is that for the potential value, you will see that it will show exponential decrease. So not like a Helmholtz model where the potential value shows a linear decrease as compared to Gauss-Chapman. And finally, we have a Stern model. Stern model is a combination between Helmholtz model and also Gauss-Chapman. Okay, so this actually accounts for both condition, migration, and also diffusion. So what happened in Stern model is that it is a combination of migration. Migration occurs first, electrostatic interaction occurs first, and then after that, followed by diffusion. Okay. So as I mentioned earlier, first layer of solvated ions of finite size is actually account for the electrostatic interaction for Helmholtz. And then the subsequent layer, as point charts, is actually accounts for the diffusion. Okay, so that is why I think for the potential values, okay, if you notice, it will show initially a linear drop, and then after that exponential drop. So other modes of Stern model will be depends on the types of electrolyte that we will use. The first one is actually a charge reversal if we use a polyvalent atoms in the electrolyte, and another one overcharge. This actually in the case of if we use surfactants in our electrolyte. All right, so the consequence of double layer, as I mentioned, the species are too distant to react, and then the driving force for the reaction is the potential drop across the Helmholtz region. Okay, and finally, the concentration at the bulk solution is different than the concentration in the on the surface of electrode. So that is why I put there the concentration of ion at outer Helmholtz plane is not equal to concentration of ions at inner Helmholtz plane. Right. Any questions so far? Anything that you want to ask? Anything you want to clarify? All right, so I think today we are going to resume our lesson. Basically, before we go to active polarization, just to get you understand, a metal on the electrode surface are in the energy well associated with a lattice structure. And in order to pass into the solution, they have to overcome activation energy. All this actually have been explained earlier. From a product that you want to produce, from a reactant that you want to produce a product, it needs to overcome a certain energy level that we call it as activation energy, EA, or delta G asterisk. So EA and delta G asterisk is actually the same thing. And then if you look at the interface itself, so you can actually see over here, okay, that at the inner Helmholtz region on the metal, basically amount of energy or potential from metal to solution is need to be overcome. All All right, so the charge transfer potential, which is actually related to activation polarization. Activation polarization or charge transfer control occurs when some step in the half cell reaction controls the rate of charge transfer. So this is actually important, where in kinetics, all reaction occurs. I mean, in order to determine the overall rate of reaction. So if you notice over here, the half equation actually showing you metals in lattice structure, okay, will be oxidized and form hydrated in solution. Hydrated means aqueous phase plus with Ze. Ze is actually the electrons. All right. So for any polarization step, you should consider a chemical reaction or corrosion reaction. Metals, double hit arrow, a forward reaction is actually oxidation process, and reverse reaction is basically reduction process that will produce metal plus, okay, metal ion plus with Ne, or the electrons. We assume that metals and metal ions are stable, so there will be no competing chemical reactions that will occur. The equilibrium of this reaction can be categorized or characterized by Nernst equation, because the reaction sometimes cannot be done at the standard condition. So the representation of Nernst can be, I think, shown as follows. Okay, so since you you know that, okay, oops, change my pen. Okay, right. So since you know that this will be your product and this will be your reactant. So the next representation, of course, like K, you have like the product to reactant. And then when you substitute over here, okay, because this is actually the term E cell is equal to E naught cell plus with RT over F, and F ln K. So when you substitute K, this actually equals to the concentration of ions over the concentration of metals. So the cell potential is directly to the concentration of metals and also the concentration of metal ion. At equilibrium, no net of current flow, then the anodic current will be equals to cathodic current. However, there will be a dynamic equilibrium at electrode surface, where both processes will occur at the equal rate, so the net charge change in the solution composition. So basically this at equilibrium process, so you have like equal amount of forward reaction and also equal amount of reverse reaction. Equal amount of current produced for forward and reverse reaction. Okay. Then you have like the total current, the exchange current density will be equal to I naught. Okay. So I naught is actually known as exchange current density. Okay. Since current is dependent on the area of electrode, we normalize current and examine current density. Okay. So current density is basically this one. If you still remember in chapter 3, okay, current density is noted as small I, that is equal to the current over area. Okay, this one is, we call it as current density. So at equilibrium, okay, exchange current density will always going to be zero because the forward reaction, the anodic current density, the amount is actually positive and reverse process is negative. So if you add all, together, it becomes zero. Noted by convention, okay, anodic current density produce positive current and cathodic current density produce negative current. As what I told you, anodic is a positive current and cathodic current produce negative current. So what will be the significance of current density? This is actually part of the thing that you need to remember. So quantitative measure of amount of electron transfer activity at equilibrium. If you have larger current density, then much simultaneous oxidation or reduction process will occur. Then the kinetic will be faster, okay? Then you will have corrosion rate higher. This is actually in accordance to Ohm's law. So if you have like higher current or current density, this actually will result you more oxidation or reduction process, then this also give you a higher rate of reaction or kinetic, and this also will result a higher corrosion rate. Okay, so what happens if you have a smaller exchange current density? Smaller is actually in opposite. If you have a smaller current, then it means a little or simultaneous oxidation or reduction process occur, very small, okay, and sluggish kinetic, very slow, slow kinetics. Okay. It is to be noted that exchange current density is always associated with equilibrium condition. That is, the rate of a forward reaction equals to the reverse reaction. Then the net of the current will equal to zero. Right. So if no potential difference between the metal and solution, the rate of forward reaction will be as follows. M will be Mn plus Ne will be purely chemical and written in equation 8. Okay, so this is actually if you have no potential difference, then the rate for forward reaction will be as follows. This is what we have seen earlier. Rate of forward reaction is equal to Kf times with reactant, and when you substitute K is basically A exponent minus delta G asterisk over RT multiplied with reactance. So since M is solid, then the reactant will be equals to 1, okay, because it doesn't have any concentration. Then your rate of forward reaction will become as follows. RF is equal to A exponent minus delta G asterisk over RT. If the potential of a metal solution, metal to a solution interface is made more positive, remember this, this is actually the condition that we say that the potential of metal to solution, we make it more positive than the equilibrium potential, okay? Sorry, the potential than the equilibrium potential. By removal of charge, the energy of M will be increased, and thus will result an increase in the rate of anodic reaction. So this is actually true, because if you actually increase potential, make it more positive, then this actually you have like more forward reaction, isn't it? Because you actually increase more potential over here, then the reverse reaction will be smaller. Of course, this one will tell you that the anodic current density will always greater to the cathodic current density because we already adjust it to become more positive. Okay, and this is actually known to be anodic Anodic polarization means that the applied potential, okay, is greater than equilibrium potential. Okay, For example, if you have metals like iron, the equilibrium potential or the standard potential will be equal to minus 0.4 volts. Okay, so if you connect it to some rectifier or supply, you actually can control the potential value. You make it more positive. Okay? You increase it to more positive. So what's going to happen? You have more oxidation process, more forward reaction, more oxidation. You see that the metal will have more mass loss and others. Okay. So in this case, for the electrochemical reaction, equation 12 must be modified to take account the energy associated with the path of current. Okay. So for 1 mole of Mn plus with charge of Nf pass through a potential difference, the energy associated will be equals to NFE. Okay. Thus, the electrochemical rate constant for the anodic reaction, this is actually for anodic polarization or a forward reaction, is equal as follows. Kf, okay, is equals to A exponent minus delta G minus N alpha Fe. So we actually add NFE because we know that for 1 mole of Mn plus, it is actually related to NFE. Right? This is actually following Faraday's law. So we substitute over here, then this actually will equals to minus NFE. Okay, and over RT. So alpha is basically a symmetry factor of the activation energy. I'll show you after this where is it. Where is alpha? And alpha is also the symmetry factors, a transfer coefficient that represents the fraction of energy that has been used to reduce the activation energy of the reaction. Okay. So if actually I expand this, yes.
Is the energy associated is equal to negative NEF minus NEF or plus NEF?
What is it again, Mari?
So you said the potential difference E, the energy associated is equal to NEF. NEF or minus NEF?
Oh, you
Third
mean like
line.
this one? This one?
Yeah, yeah. Up. Doctor, the third line.
Third line. Which one is
Yeah.
this one? This equation? Equation 13?
Pass through a potential difference E, the energy associated is equal NEF. Is it equal to NEF or minus NEF?
Oh, this one.
Yeah, this one.
You mean this one? Okay.
Yeah.
Oh, yes. It's actually equals to minus NAF because we know that in Faraday's law, delta G is actually equal to negative NFE. Yeah, I think I forgot this one. So that would also like explain this one. Okay. Thank you very much, Madi, for noticing that.
Yeah, thank you, Doctor. Not at all.
All right. So when you expand it, okay, so if you multiply, this one with this one and then expand it, then you will get another term as this, okay? So the term will be the forward rate, Kf is equals to A exponent minus delta G asterisk over RT, multiply with exponent alpha NFE over RT, okay? And since this actually, the first term that we have looked in equation 8, if I'm not mistaken, we can actually summarize or change it into this term, okay, and then it will become Kf using electrochemical method equals to K forward of chemical reaction exponent and alpha Fe over RT. So the electrochemical rate for anodic reaction will later on become as this. Okay, RF, okay, for electrode is equals to A exponent minus delta G asterisk over RT exponent alpha and Fe over RT. Okay, so the electrochemical rate for anodic reaction, okay, or a forward reaction. So this is actually the energy diagram, right? At equilibrium, okay, you'll see that equal amount of current will be used, okay, to produce a product. Okay, so the similar amount, alpha is actually the symmetry factor, as I said, from reactant to the intermediate or the optimal or the transition state. And then 1 minus alpha is actually the reverse symmetry factor. Okay. And if actually you consider anodic polarization, this is actually for anodic polarization, you will notice that the amount of alpha is greater. Okay. The amount alpha, not amount alpha, the amount of delta G asterisk is greater because it is no longer the same. Not equal amount of current is being produced. So at one side, especially at the anode side, or the conversion from reactant to the transition state will be higher. You need more energy to overcome. Okay. And since the rate of electrochemical reaction is directly proportional to the current density, okay, thus for anodic reaction M to Mn plus plus Ne, the anodic current is given as follows. Okay, so we are using this formula. Okay, rate is equals to current density over Nf. All right. So rate, what is rate? I think rate earlier we have seen that rate of forward reaction is equals to A exponent minus delta G asterisk over RT. So when you substitute to this one, because you know rate is equals to current density over Nf, you substitute this part into this, then you will get current for anodic is equals to Nf A exponent minus delta G asterisk over RT. So this is actually the same thing, right? And then the delta G asterisk of activation, the anodic will be equal as follows. Because over here you will see that, as I said, since we are doing anodic polarization, the delta G value will be higher than delta G for anodic is actually equals to delta G asterisk. This is actually delta G asterisk. Okay, plus with 1 minus alpha, because this is actually the factors 1 minus alpha. Both is still, I mean, like having NFE minus with NFE. Okay, right. So if you simplify it, actually you will get like delta G anodic is actually equals to delta G asterisk minus alpha NFE. Okay, all right. So if you substitute this one into this one, okay, you will get the final term actually equals to this. Anodic current density equals to NFA exponent minus delta G asterisk over RT exponent alpha NFE over RT. So you can try later on, I mean, like substitute NFA exponent minus delta G. Oops. RT exponent alpha NFE over RT. Okay, all right. So this is actually the anodic current density derivation. I mean, from this simple equation, you have like M to Mn plus E, and then you know that the forward reaction RF, because this is actually Kf, is equals to A exponent minus delta G over RT. Okay, and then after that, you substitute into this formula, okay, or this equation, then you will get this. And delta G, as I said, anodic activation energy, because it's already like increased, so you have an increase over here. Then the initial at equilibrium is actually equals to G. So the one that I circle over here, this is actually at equilibrium. And this is actually at equilibrium. Okay, this is basically the changes. Okay. Anodic polarization. Okay, so anodic polarization, then you have a new term for your anodic activation energy, right? So once you rearrange, you become like this, and you substitute into the final form, then you get this, right? So what about the cathodic current density? The cathodic current density can be derived similarly, because you have, in this case, a reverse reaction, M plus Ne. Now it becomes Kr, reverse rate, equals to M. Okay. So the rate of a reverse reaction is basically Kc over Mn plus. Okay. So when you actually substitute into this equation, the Faraday's law, you can get actually IC that is actually equals to A exponent minus delta G over RT multiply with M plus. Okay. So you notice over here. The only difference is that for anodic, we didn't actually account M, because as I said, M is actually metal. Metal doesn't have concentration. But for reverse reaction, you have ions, right? So you can account this. This part is actually the same as this one, except that it has a multiply with the product, which in this case Mn plus. Other thing will be the same. Okay, the cathodic activation energy is equals to delta G plus with 1 minus alpha NFE. Then when you substitute this into your current density equation, you will get the final term will be equal as this. Okay. Any questions so far? Anything that you want to ask? Anything you are not clear with this derivation, anodic current density and also cathodic current density? Ada soalan? Anything?
Clear so far, Doctor.
All right. So after all, we have talked about anodic polarization and cathodic polarization. Cathodic polarization, before I forget, it means that you have like more reverse reaction. Okay. Cathodic polarization, like more reverse reaction, okay, which actually giving you more reduction. So in this case, for cathodic polarization, you have cathodic current density that is actually bigger than anodic current density. Okay, all right. Some might like ask, I mean, how we can actually change the anodic polarization or cathodic polarization naturally or something. So if you understand, if I said anodic polarization means that you have more forward reaction, you have more oxidation process. So by, I mean, naturally you can increase forward reaction by adding more oxidant, like oxidation chemicals, potassium permanganate, anything that have more oxygen, then this actually can promote more oxidation process. Eventually, you can also increase the potential value and making it behaving like having more oxygen and experience more oxidation process. Meanwhile, for cathodic polarization, okay, if you add like reductants, like you increase the concentration of acid, you have more H plus, then you know that you have more reduction process. Okay? Then this also can be contribute to the cathodic polarization. Okay, polarization and overpotentials. We have, I think, explained a lot about polarization. So what is actually mean by polarization and overpotential? So polarization actually defined as the change of open circuit potential as a result of a path of current. In practical situation, polarization sometimes defined as the potential change away from some arbitrary potential and often the mixed potential of a free corrosion potential. Okay, the polarization can be expressed as the change of potential. Okay, and the value that you will obtain is actually equals to overpotential. All right. So as I said earlier, I give you the examples of iron in a solution. Fe in a solution, when it corrode, the E naught or the EOCP, the open circuit potential, will be equal to minus 0.4 volt. All right. So the changes, okay, anodically or cathodically is known as overpotential. So imagine if you have like current to potential curve, like I mean a plot like this. So you have like one point over here. This is actually your open circuit potential value, and you increase the potential value positively. This is actually anodic polarization, and you actually study the behavior of the current. Probably you will get like some increase in terms of the current value. Okay, and then maybe if you change the potential value cathodically, okay, you can also have a behavior that it forms like a decreased linear or something like that. Okay, or if you have like a lot current versus potential, then if this is your EOCP, this actually at current 0. Okay, so this is actually log. You can have like an increase of the uh, if you do like anodic polarization, and also a negative linear, okay, if you do cathodic polarization. So the change of potential, because this is actually the equilibrium. Remember that equilibrium potential is also equals to opposite potential. Okay. All right. So this is actually the applied potential, AP, EAP, EAP, right? So the change of potential, this one, is actually equal to applied potential minus with equilibrium potential. So this actually will give you a value known as neta, or overpotential. So this is actually neta anodic, and this is actually neta cathodic. Right. Electrode reaction are assumed to induce deviations from equilibrium due to the pass of electric current through the electrochemical cell, causing a change in electrode potential. This phenomenon is known as polarization. Okay, as I said, induce deviation from equilibrium. This is actually the induce. We actually increase the potential value by force, not naturally, by force. Due to the pass of current, we set it on the potential state, we increase the potential value, okay? And causing there's a change in electrode potential. This is known as uh, polarization. The deviation from equilibrium causes an electrical potential difference between the polarized and the equilibrium, which is the unpolarized. And this is known as overpotential. So the value that you will get, okay, after you have increased the potential value, okay, applied potential minus with the equilibrium potential is actually noted as overpotential, right? So as I explained earlier, polarization is the change from equilibrium of half cell electrode potential caused by the net of surface reaction rate for the half cell reaction. So we have two modes of polarization. We can have anodic polarization. Okay. So anodic polarization means that you have more forward reaction. More forward reaction means that you have more oxidation process. Right? Then you will see over here, you have like anodic current density is actually greater than cathodic current density. And in this case also, the applied potential is going to be bigger than equilibrium potential. Because the values of potential produced over here is more positive. Okay. Right. So we have seen in the equation, you have like more forward, the arrow will be bigger. And then for cathodic polarization, it means that you have more reverse reaction. This actually means that you have more reduction process. And when you have like more reduction, it will be more negative. The potential will be more negative. Cathodic current density will be bigger as compared to anodic current density. the equilibrium, okay, potential will be bigger than applied potential, because the applied potential will be more negative, so it's smaller as compared to equilibrium potential. Right? This is actually to summarize cathodic and also anodic polarization. At equilibrium, you have an equal anodic and cathodic current values or reaction. Meanwhile, for anodic polarization or cathodic polarization, you have a different values of current density. All right. So overpotential, what is meant by overpotential? Overpotential defined as the difference between the actual potential and the equilibrium potential. So always remember that here in this equation, neta is actually equals to applied potential minus with equilibrium potential. Okay, so neta can be positive in case of it is a anodic polarization when applied potential is bigger than equilibrium potential. This in the case of anodic polarization. And neta can be negative when applied potential is, smaller as compared to equilibrium potential. This is actually in the case of cathodic polarization. Right. So earlier on, we have seen equation 17. This is actually the anodic current density, okay, that we have derived. So substitute E. E is actually the applied potential, or E cell. So don't be confused. E applied is actually equals to E cell. Not E naught, E cell. Then you can actually substitute it over here. Because this one, if you rearrange, the applied potential will equals to neta plus with equilibrium potential. Okay. So when you substitute, you will get this term. You actually have one part that have equilibrium potential. You will also have another part which is actually the overpotential. Similar thing for cathodic current density in equation 21. You can substitute this part with this equation, and you have also two parts. You have like one part on applied potential, equilibrium potential, and also another one is actually for overpotential or neta anodic. So at equilibrium, we assume that anodic current density and cathodic current density is equal. So if you put like these two things together, equal, then you can actually cancel off few things. Then at the end, you will get a few terms only. This one and also this one. Okay. So for anodic current density, if you simplify it, it will become I naught. This I naught is actually the exchange current density exponent alpha NF neta A over RT. And for cathodic current density is equal to I naught exponent minus 1 minus alpha N F neta A over RT. Okay. So since anodic current density, which is actually measured current density for anodic polarization, is given to anodic current density minus with cathodic current density. Okay. Thus, for anodic reaction, you can actually substitute this term, okay, this one to this one. Okay, because it's minus. Then you will get a term. Okay. So this term is actually known to be Butler Volmer equation derivation. Okay. So if you like actually simplify it, you will get this term. Okay. So things that you need to remember is that Butler Volmer equation is very much important. Okay. For you guys, especially you need to know how to derive this Butler Volmer equation. This, as I said, important. You need to memorize the step how you can actually derive this equation, because it's one of the favorite question asked during exam. Derive Butler Volmer from m to mm plus ne equation. So you know that you have to start from rate, rate forward, alpha A exponent minus delta G RT, and then you know that rate is equals to I over NF, and then you substitute the value, and finally you also substitute potential equals to neta plus with equilibrium potential. Then you will get these few terms, and finally you can get Butler Volmer equation. So I guess as a homework today, okay, I will upload. I will put an event in your e-learning to for you guys to derive Butler Volmer equation. So please derive Butler Volmer equation from the forward and also from the reverse reaction. Okay. So it's just a practice for you guys. You can start from this one, and then you, as I said, you can start with the rate of forward, rate of reverse, substitute this into, the rate formula, and then substitutes also the overpotential notation, and finally you can get this. Okay. Any questions so far before that? Anything that you didn't understand or you want to clarify? Anything? Diana, okay ke?
Tengah hadap lagi doktor.
Okay. As I said, in KAA 504, especially for my part, there's actually maybe, I believe, two equations that you need to memorize how you can derive. The first one is actually Butler Volmer equation. And then, another one is actually Tafel equation. Okay, so only two equations that you need to memorize how you can derive. As I said, it's starting from this reaction, then you actually write in a forward rate, reverse rate, substitute in this notation, then you get the terms and everything, okay, and then you put the overpotential terms, and you finally will get this. So this is actually the Butler Volmer equation. Okay, so the Butler Volmer equation is very much important for polarization, especially next chapter. We are going to learn about the electrochemical methods using potential dynamic polarization, which actually later on we will try to relate this formula, the current density measured, the measured current density, or the I core, and the corrosion current density is actually measured using this formula. Right. Butler Volmer equation is one of the most fundamental relationship in chemical kinetics. It describes how the electrical current of the electrode depends on the electrode potential, considering that both anodic and cathodic reaction occurs at the same electrode. Assuming the concentration at the surface is equal to the concentration of the bulk, which will be the case of equilibrium condition, okay, three variables, okay, alpha A, alpha C, and I naught, need to be determined to use Butler Volmer. And Butler Volmer equation gives a good representation of experimental data for many systems. The exchange current density is a strong function of temperature, and when the exchange current density is large, the reaction is said to be reversible. When the two reactions take place simultaneously on the same electrode, we can use Butler Volmer equation for each of them. So earlier, I think I have explained to you about overpotential. You have like at current zero. This is actually at current zero. You have a potential increase anodically. This is neta A, and this is actually neta C. This is actually plotted against potential on y-axis and current on the x-axis. You can also have like current on the y-axis and potential in the x-axis. It doesn't matter. It doesn't have any fixed plotting. Okay. So like this one, you will see that as we increase the potential, it means that we actually observe a linear increase in terms of the current density value. Meanwhile, if we actually decrease the potential, what happens is you have a decrease of current as well. Okay, right. So the Butler Volmer curve, right, like this one, is often named as LPR, right? Linear polarization resistance. Why it is named as linear? Because the plot is actually showing like almost linear. Polarization, because of the phenomenon, we actually experience anodic and also cathodic polarization. Resistance, where does this resistance come from? Because if you look over here, it is actually potential versus current. Okay, then if you actually calculate the slope over here, okay, slope, slope is actually equals to the change of potential over the change of current. If you remember Ohm's law, V is equals to IR, or E is actually equals to IR. Okay? So R actually means that you have potential over current. So this is actually what it means. Okay. If you calculate the slope, this actually will give you RP, polarization resistance. Because following the laws of Ohm's law, okay, so you get like RP is actually equal to the change of potential over change of current. LPR and RP, I guess we are going to learn it more detail in chapter 5 in terms of the technique, because this is also a technique. And we can also make the linear plot into logarithmic plot. So this is actually a log version. Current, you make it log, then it will become like a Y or T shape of curve. And this curve is known as Tafel plot. Tafel is the name of a person. Okay. So same thing, actually you are looking at anodic side and also cathodic side. You have also an anodic current and also cathodic current. This actually indicates that half of this actually for anodic reaction, oxidation, to be more precise. And then another half is actually for cathodic, which is actually for reduction. So as I said, also the narrow region of the small overpotential, the relation become linear. Okay, if you zoom over here, you will see that it's at the current zero, it's almost like linear plot. And this is where you can actually calculate the slope in order to find the resistance value. All right, so we are moving on to the next part. Once we have like, derived Butler Volmer equation, the first term in Butler Volmer always describe the forward reaction. because this part is actually coming from anodic current, because as I said, if you still remember, measured current density is actually equals to anodic current density minus with cathodic current density. So this is actually one part from anodic, and this actually for a forward reaction, and another part is actually coming from cathodic side. Okay, reverse reaction. Relating the net current density of electrochemical reaction to the overpotential, it can be seen that when overpotential is equal to 0, okay, when you make this equal to 0, the measured current density is equals to exchange current density, because this one is equal to 0, you multiply everything with 0, you only get this. Okay. And the anodic process equal to that of the cathodic process. Okay. So meaning that both process actually at equilibrium lah. Okay. When neta is equal to 0. However, if the neta or the overpotential value is positive, the first term will increase exponentially, while the second term decrease exponentially. So this actually justify from this plot. Okay, you will see that if we have, a positive overpotential, then it will increase exponentially. If you have in contrast, you have a decrease in current exponentially for your cathodic side. All right. Then at neta is more than plus 0.05 volt, the second term can be neglected. Then if neta is bigger than 0.052 volt, the equation can be simplified as follows. What does this mean? It means that if you have a potential that is more than 0.052, 0.052, this actually accounts for your RT and F. RT over NF in your Nernst equation. So you will get this value. So anything that is bigger than this, okay, the second term can be neglected, okay, which means the cathodic term can be neglected because you will have like more increase at the anodic region. So it will be simplified as this. We remove this part. And if the neta is lower than minus 0.052, then the first term can be neglected. This is actually in the case of if you do cathodic overpotential. So if you do cathodic potential and it is actually lower than minus 0.052 volt, then the first term can be neglected. You have like more dominant cathodic reaction or more dominant reverse reaction. Taking logarithm in equation 32, sorry. Okay, so you will get this term, right? And then converting, okay, ln to log. So you will actually multiply it with a factor 2.303. Then you will get this term, this equation 35. Equation 35 can be written in general form as this. We actually categorize this as or classify this as A. This one, this term is B. Okay, right. So I guess maybe some of you are afraid to see like a lot of symbols and everything. All symbols are actually just symbols, nothing to be afraid of. If you didn't like to use like alpha, beta, and eta, what you can use other symbols that you think is more suit for you. You can use like pineapple, elephant, Doraemon picture, whatsoever. It's just a symbol to indicate something, right? So this equation is known as Tafel equation. The Tafel equation is actually this one, that you get this beta A and beta C. This is actually Tafel equation. How you can get Tafel equation is basically from your Butler Volmer, okay, and then you make it into log. You make it into log, and then once you rearrange the term, you rearrange the term. Okay, you just make it into like this one, because this one we say beta A is actually equals to 2.303 RT over NF, alpha NF. This is just a term. Beta anodic indicate this. So you just replace it with this, and you will get the term. Beta A is equals to beta A log IA over I naught. Meanwhile, for neta C is equal to beta C log IC over I naught. Right? So this is actually how you can get Tafel equation. This is the second equation that I want you guys to know how you can derive these things. So as I said, in your homework, you should write how you can derive Butler Volmer equation, and also how you can derive Tafel equation. Any questions so far? Anything that you are not sure? Ada soalan?
Sir, can you get back for the page 33?
Sorry again, Madi?
Can you get back? Can you go back to the page 33?
One?
No, previous one?
This one?
No,
Oh, this
previous.
one.
Yeah, this.
Okay, yes.
I asked it about R is equal E over I. From where we get this law?
Where we get this law?
Yeah.
As I mentioned to you, it is actually according to Ohm's law.
Oh, Ohm's law.
Yeah, Ohm's law. This Ohm's law actually indicates that V is equal to IR, or potential is equal to current multiplied with resistance. If I rearrange this, making resistance as the interest, then R is actually equals to potential over current. So if you actually relate it with this phenomenon, because this is actually a graph plotted potential versus current, and it is a linear form. So if we calculate the gradient, the change of potential over the change of current, then this actually will equals to the resistance. And what type of resistance is actually a resistance polarization, because the data is actually generated from polarization values or polarization data. You get exponential increase of anodic and exponential decrease of cathodic. If you combine two together, it become like this region will become a linear.
No. Thank you.
Any other question? Anything? Mariam, boleh faham ke?
Tengah digest lagi, Doktor.
Nak kena digest dulu. So that is why I think the importance of writing the Butler Volmer, just to get you used to it, to get you understand the concept. Okay, and the same thing I think for Tafel, how you can get the Tafel. But Tafel, I think derivation is quite simpler, because you can start it from Butler Volmer. So you just account maybe on anodic or also on cathodic. So you have terms for neta A and also terms for neta C. So if you actually simplify it, this is actually simplification. Otherwise, you will write it in full. But since we can simplify it, so we just say that beta A is actually equals to 2.303 RT over alpha and F. Then when you substitute it, it will be simple. So this is actually the Tafel equation, right? Just to extend a bit about the Tafel equation that we have seen slightly so far, if the overpotential is large and positive, the second term can be neglected. This is actually what I've told you earlier. If the overpotential is greater, okay, greater than 0.059 volts, then the second term can be neglected. You only have the first term of Butler Volmer, which is the forward reaction. If the potential is large and negative, means overpotential is actually lower than minus 0.059 volts. Then the first term can be neglected. You have like more dominant or major reverse reaction. Okay, so you will have in your Butler Volmer terms like this. So taking into logarithm, okay, for equation 32, just show you the equation 32, you log it, okay. So what happened is that okay, so you know that then the bottom, I mean the I measured will be equals to current density okay. All right, so if you log, I mean make it into log, you ln it. So what happened is it become like ln x1 will be gone. Okay, so the same thing as this one. And if you rearrange, because as I said, we just make it a simpler things. Neta A, this one is actually equals to beta A. Okay, so we change from ln to log. Then you have this term. Okay, so if you substitute, it become simplified as this. Beta A is equal to beta A log IA over I naught. And for neta C, if you actually do the logarithm of equation 33, then you will get these terms. Okay. So if the question asks you to derive Tafel equation, you need to show how you can get neta A and neta C with beta A and beta C notation. Don't show only one lah. I mean, show both for anodic and also for cathodic. Okay. Any question so far? Anything you want to ask or what? So earlier on, I have mentioned to you about Tafel plot. So Tafel plot is basically the plot of log current density versus potential, or it can be vice versa lah. Potential versus log current density. Okay, current density. So over here, you can notice that it is plotted potential versus log I. So it forms like this shape, normally like T shape or Y shape. So this actually means that you have anodic overpotential, you have a linear increase, and for cathodic overpotential, you also have a linear plot over here. So what kinds of information that you can get from here? Okay. Earlier on, we have talked about a Tafel slope, beta A and beta C. So beta A and beta C is actually the slope for anodic and also the slope for cathodic line. I just make it in reverse lah. Log I versus potential. Okay. The plot is actually created when you have like two linear graph connected together. This is actually point that you will get your equal. Okay. If you do a tangent of your Tafel plot, you will get your I core. or the measured current density. So this will be your beta A, and this slope will be your beta C. Okay. So all this actually would be useful in calculating corrosion rate later on. I mean, because if you do potential dynamic polarization methods, you will get this graph and you will determine what will be the I-core. And from I-core, you can use a formula to calculate the corrosion rate. This is what we have seen in chapter 3 as well. 0.13 multiplied with I-core multiplied with equivalent weight over density. So it is actually recorded from your Tafel plot. So how you actually get the Tafel plot is actually due to polarization studies. You do overpotential anodically and cathodically. Then it will give the plot. This actually will give you a behavior the behavior of the metals that you will see if you increase the potential or if you decrease the potential. It is generally used to when the overpotential is at least 500 to 100 millivolt. The Tafel slope varies between 30 to 300 millivolts over decade. The same thing, sometimes people also call Tafel plot as Evans diagram. Both are actually the same thing. Evans diagram in turn is just like a V shape, okay, not like a Y shape. But both are actually the same thing. It's just that for Evans diagram, it's more linear, like linear anodic and linear cathodic. All right, so this is actually the example. If you have an activation polarization of hydrogen reaction, where at equilibrium, when no current flow, the reaction potential is actually equals to 0 volt at the standard condition. And the exchange current density is equals to 1 milliamperes over centimeter square. If the current is allowed to flow with the potential change, the overpotential can be predicted by Tafel equation. So for beta A, that is equal to 0.1 volt over decade, and current density that is equals to 10, okay, the neta A is actually equal as follows. So you can actually calculate based on the Tafel slope equation. So the Tafel slope equation that you have seen earlier is that neta A is equal to beta A log IA over I naught. Okay, so over here, the exchange current density is given as 1. Okay, and then the other information is that beta A is equals to 0.1 millivolt over decade. This is actually the unit for beta A and beta C, and the anodic current density. So actually you can see over here, okay, anodic current density is equals to 10. 0.1. 10,
Doctor,
0.1. Yep.
Doctor,
Yes.
can you attend Mahdi?
Can what?
Can you attend Mahdi? He lost his connection and back.
Oh, okay. Sure.
Right.
All right. So I just repeat, earlier on, we said that the anodic current density is equals to 10. So what would be the beta A value? So you say over here, 10. Okay. Then you get over here, value is actually equal to 0.1 volt decade. And then if you also want to calculate beta C also, value will be minus 0.1 volt. So we just substitute into the equation. So what you will get is that 0.1, because this is actually the current, the potential values that you get, 0.1 here, log anodic current density, which is actually equal to 10. Exchange current density given is actually equals to 1. So if you calculate altogether, you get 0.1 volt. All right, I guess maybe a last slide for today. I wouldn't go further, just to let you guys to digest whatever we have learned today. I know it's quite a lot, but it needs to be done. It needs to be, I think, studied. So a partial anodic and cathodic reaction of a corrosion of zinc in acidic media. Okay, so how to relate the corrosion of zinc in acid with polarization data? Okay, so we imagine that we have zinc in an acid solution. The oxidation process, of course, will be the formation of zinc 2 plus 2 electron. This actually occurs at anode. Okay, and then the others will be the formation of hydrogen gas. This is actually the reduction process. The 2 electrons produced from anode will be transferred to cathode, okay, to produce hydrogen gas. Right. So standard potential of zinc is actually equals to minus 0.7 volt. Right. Imagine that if I have log I versus potential. This is actually in the case of Tafel. I just make it into Tafel plot. You have minus 0.7 over here. And then we increase the potential anodically. You got another linear. Decrease the potential cathodically. You got another linear. So you get something like this. Okay, a plot like this. So this line is actually accounting for the anodic reaction. Zinc 2 plus 2 electron. Meanwhile, this line is actually accounting for formation of hydrogen gas. Okay? All right. So what you can get in the end, you can get this one. This is actually noted as equal. This thing over here is actually noted as ICO. Oh. If we look on the linear polarization plot, it's not log, it's just normal current density versus potential. So at the current zero, this at the current zero, this will be your equal, okay, minus 0.7. You have one exponential. Okay, this is actually indicating that you have theta A, and another one, okay, decrease exponentially if you actually decrease the potential, so you get this one. All right, so where will be the I core? So the I core, of course, if you actually take the tangent, okay, this will be the difference, and this actually will be your I core. Okay, so the first exponential curve is actually account for zinc to zinc 2 plus. And another one, the decrease of exponential is actually for the formation of hydrogen gas. So basically what it tells, when you do polarization methods, you can actually study the behavior because if let's say that you have some fluctuations and some abnormalities in the linear plot, then you know what is actually happening. Probably there's some disturbance, there's some interference in either anodic side or also cathodic side. Because from here, you can see the response. If it is not linear, if it's just like forming like a flat region, which we will learn in the next class, will give you the clarification. Okay. All right. So, do you have any questions so far? Anything that you want to ask regarding on Tafel plot or linear plot? Anything?
Doctor,
Yeah.
I would like to ask on the Tafel plot, events diagram, the
Mhm.
slide before this one.
Which one?
Yes, this one.
Yeah.
So at last we will get 0.1 volt, right?
Mhm.
So it is depends on B alpha when we have when we have B alpha at 10, right?
Yeah.
I mean IA at 10. What if we
Okay.
have cathodic? Can it be?
You mean neta C?
Yes, let us see.
If you actually calculate, you will get the same value.
Um,
You didn't get the same value?
I didn't try it.
Oh, yeah.
I
But
mean,
basically, you will get. Because basically, if you get like, I mean, for your neta A, if it is like equal polarization, I think potential range, then you will get like the same distance, like for neta A and also neta C. So more or less, you will get like almost the same value. So this is just to show, I mean, the correlation. I mean, like. Whether you can get neta A and neta C using Tafel equation. But as I said, if you actually calculate or find the beta C, okay, and then after that substitute in the formula for neta C, you still get the same value. You will get 0.1 as well.
oh, okay.
Is this at equilibrium?
Sorry, what?
I said, is this at equilibrium?
Actually, to say that it's equilibrium is not really Mahdi, because if it is in equilibrium, it will be zero, because at equilibrium, no overpotential occurs. Overpotential occurs means that you actually varies the potential value and you will get different current value. You will have like increase in anodic current if you increase the potential positively. You will have like a decrease in current density if you actually decrease the potential cathodically.
So, Doctor, how can be both of them are equal if are not in equilibrium condition?
How come it is not like what?
I said, how can be equal the same value if they are not in equilibrium condition?
Because Mahdi, if you notice the current, I mean, of course, I mean, this one, in this case, if you say that it is in equilibrium, we can say yes, because the current values will be equal. I mean, like here, the current value for anodic is equal to 10, the current value for cathodic is also equal to 10. Then yes, I mean, we will get like in equilibrium because the current of anodic and cathodic is similar. But get the value. To get like this curve, it is not like uh, it is automatically in equilibrium. We still need to like do the overpotential. It's just happened that because of we perform at the equal range of potential or overpotential, then we should get like slightly almost similar current value for anodic and also for cathodic. Okay,
Okay,
Madi?
I got it. Yeah, I got it.
All right. Any other question?
Doctor.
Yeah.
Is it possible if like we change the like beta cathodic to be negative 0.1 volt?
Negative because the plot is negative linear. But if I mean, if you actually calculate some, maybe you will get negative value. But since the plot is basically a negative linear, then this is actually what we expect. The value will be negative. But if we actually assume that it is, I mean, we didn't actually account the symbol, then it will be the same.
Okay. Okay, thank you, Doctor.
Okay, you're welcome. Any other question? So actually on Tuesday, I told you that we are going to have, I think quiz, right? For today. I think for today, we are going to take a break from quiz. Maybe we are going to have it next week, but together with the parts that we already studied. So I guess what I will create in your e-learning later on will be the slightly a homework, how to derive Butler Volmer and also how to derive Tafel equation. It's just a practice for you guys as a guide. Later on, how what will be the first step if you want to derive this equation? So at least you know, and at least you are familiar with all symbols and also all equation, right? So we are going to continue with the other parts, concentration, polarization. I believe the other parts we can basically finish it by next week, Tuesday, and we can start a new chapter on Thursday. So maybe last question, if you guys have a last question, anything? All right, so if there's no question, then I think I will adjourn the class. I believe today is very heavy for you guys. Many things, many output coming in, many formulas. And maybe you need some time to digest it. I totally understand that. So thank you very much again for your kind attention, and hope to see you next week on Tuesday. So have a good day, have a good weekend, and Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam.
Thank you, Doctor.
Thank you, Doctor. Assalamualaikum.
Thank you, Doctor.
Waalaikumsalam. Yeah. Welcome.
Waalaikumsalam.
Waalaikumsalam, Doctor. Thank you.